Hi guys, this is Mist. It's been a while, but I thought today would be a good day to show you what I've done in the past year in terms of Redstone graphics hardware. Now, if you're not familiar with my Redstone graphics project, a lot of it uses serial-based circuitry. And this is not stuff just as simple as registers and such. It goes very deep into parallel line calculators to serial-based 3D transform units and such. But I'm going to show you all the steps that it took for me to get to this point where I am able to render wireframe objects. And hopefully soon I'll be presenting fully textured objects. But anyways, let me go ahead and go to the first build that really kicked off this little adventure of mine. All right, so really the first build that kicked off this project was this parallel line drawer. Now, the parallel line drawer uses a very cheap line calculating algorithm where it does recursive midpoints. Now, if you're unsure kind of what that means, I'll go ahead and hop in Desmos real fast and just give you a quick rundown of what that is. All right, so let's say we wanted to draw a line between the points 1, 1 and 10, 20. What we could do is we could take the endpoints of x, average them together. So this is the 1x and the 10x. And you basically add them together and divide by 2. If you don't know, in binary, divide by 2 is as simple as shifting to the right. But in this case with serial, you don't need shift registers. You just delay the output either by 2 redstone ticks. Basically, you just delay it by 2 redstone ticks. So that's really cheap. So really, all I use is adding and just clever timing. Now, we did the same for the y coordinate, and the output will be this middle point here. I can label it so you can see it right there. And then basically from there, we could take this point and use it with the 2 ends. So now we split the line into 2 segments, and we calculate those 2 points between those. So we would get this point. Oh, sorry. We'd get, I gotta get this label thing under control. This point. We'd get this point. And there would have been another point up top, but I just don't have it there, so I apologize. And basically the algorithm just keeps splitting like that to an n amount of times. And what's great about doing an algorithm like this, the pros, is that the points they generate exponentially, basically. So since they keep subdividing, you just get an exponential amount of points generated every layer of this recursion. But of course, you have to have the layers fixed. So this line calculation is linear every time, so it doesn't have a variable amount of time. It has the same amount of calculation time, which is really good, actually. That means the longest line doesn't take any more time than a single point, or a tiny line for that matter, and it's pretty fast. And depending on how many pass-through decoders you have, it's pretty good. So I'm going to go back to Minecraft now. Oh, and also, I almost forgot to show that it would look like this when so you can imagine like you have all your little points generate, and then it fully converges to a line, basically. That's the idea. Anyways, yeah, we'll go back to Minecraft. All right, so I have made a YouTube video on this demoing how fast it is already. I'll put the link to it in the description, but I'll go ahead and just run this preset data of a pyramid, and I'll make sure the tick rate is just your 20. And you'll see how fast it is to even do a wireframe render at this kind of scale. So I'll just go and activate it. As you can see, I was really into observers and notebox then, but I decided to ban those to make MCH compatible hardware. MCH PRS, I believe. That's how you say it, but it's basically an accelerated Redstone server that you can have on your machine, and you can run Redstone fast. I used it a while ago. It's been a while though, so I'll have to get the newer version of it. But yeah, as you can see, at only 20 ticks per second, we can generate this pyramid in a matter of seconds, simply due to just how fast that algorithm is. It's a very fast parallel algorithm. Now, another thing that this line drawer just did is it actually split the line segments up into these little pass-through decoders so that they all can just they can all be run together at the same time, rather. So we don't have to wait a super long amount of time per line. It only takes a couple seconds per line. So that was the first line. And again, since I said it used serial, we use serial ladders. And if you look right here, this is one serial ladder. It basically looks like a 1-bit adder, except the only difference is that the carryout feeds back into the carry-in. So it sequentially processes the numbers. And you can just pack hundreds. If you had to, you could pack hundreds of these adders in a small amount of space to do the calculations quick. Alright, so now that we've covered that, I'm going to move on to the next item to showcase, which is very interesting. I think you guys will like it. Alright, so I was going to show you the device before this one, but for some reason, I think World Edit screwed it up. But it was basically just a quad drawer, but it could draw quads or triangles depending on how you input the data points. But we're going to have to skip it. Unfortunately, I don't know what happened to it. We're going to skip and go to the quad and texture mapping prototype. So this is the first one before Speargu V1. The first colored, not the first, but my first colored texture mapping unit that I worked on. So this is the predecessor, and I've shown this in a video. I'll link it in the description. But basically what it does is it first generates, I'm going to just make it very simple for explanation, but it first generates the two lines using that line calculating algorithm. So you can imagine, it doesn't draw these lines, by the way, it just generates the data points. And what it does is it stores them into these queues. So we have queues for the U and V coordinates, so that's for your texture. And then there's the X and Y queues right there. And what it does from there is it basically takes the quad coordinates and it basically assigns a 1 or a 0 depending on your texture UV coordinates output. It'll output either a 0 or 1. So you could basically draw two lines between those and like eventually draw the texture that you've saved in the texture memory input. So eventually you kind of just scan between two lines and you could draw like a face or whatever. Now, obviously it doesn't have to be a perfect square. You can have the shape tilted diagonally and it'll draw. It could be like stretched out quite a bit and so on. Obviously there's a limit to the stretching in this case because I made the hardware limited to a certain amount of data points. So depending on how the programmer uses the hardware, it can be kind of fun. But yeah, for this test, since I've already shown a video on it before, I'm just going to make the game 2 times the speed to just get it over with and show you the rendering. So I put in a creeper face and the coordinates from whenever I did this last test on YouTube. But yeah, it'll be in the description if you want to see more of the kinds of transforms I've done onto this quad. But yeah, basically it'll just, again, generate the quad using the quadrilateral coordinates, and then it'll assign a 1 or 0 depending on the texture coordinates. And as you can see, we're drawing a creeper face that's kind of like slanted. So you can think of this like, imagine you had a wall with a creeper face and you're like looking that way, for example, or something. It would look kind of slanted. But there you go. So we could draw quads or triangles with a texture on it. And the texture coordinates, you can do all kinds of things. You can take a section of the 8x8 texture, or you could draw the whole thing and then apply it to the shape itself. So there you go. So we have the texture map and quad calculation solved there. As a refresher, these are just line generating hardware, the cues for the individual lines. And yeah, and then we use some proportionality. Since there's a finite amount of data points, we can use proportionalities to assign the textures to the quad coordinates. And that's it. So we're going to go ahead and move on to the next item, which basically span off of this thing. All right, so here's Speargu V1. So basically, it's just an optimized version of that previous quad and texture rendering unit. As you can see, it's a lot flatter. Down here was just a way to store all the data points for all these different quads that I've used to make the scene. This little experimental scene, because before this, I didn't have any sort of 3D transformation hardware. I just used the mindset of, let's assume I have the hardware. What would the points look like and how would you render it? And then I also just assumed that I used some kind of painter's algorithm, so it draws in a certain order, assuming I had that hardware on the input. And yeah, it basically drew. I already made a video on this. I'll link it down below. I'm not going to run this because it takes a minute. Actually, it's a lot faster if you use an accelerated version of Minecraft, because the problem with the tick rate is the updates still kind of lag the game out, so it's not exact. But anyways, yeah, this one was pretty fast. I've already shown this on the Open Redstone server to a couple of people, and if you're interested in this hardware, you can go to my build plot. My username is the same as YouTube, so you could just visit it and check it out. Although this is a texture pack right here, so you wouldn't see this. You would literally just see redstone dots back here, as you can see. There's just redstone dots. They just have a model applied to them. So yeah. And yeah, basically all it did is it made a couple of things. I fully completed the texture port instead of having just some like redstone torches on and off at the input like the last one. So you could fully customize these signal strengths to give you a whole bunch of different textures. And of course, in the future, I plan to have texture memory, like a texture cache, so you can swap the textures out, depending. But anyways, we have, in this case, I just made like some simple textures, like a wall texture in that corner, color palette, just has all the colors, and then like enemy sprite, the zombie, and then I just rendered it. And it uses the exact same algorithm as I described before, it just has color coordinates assigned. But as you could figure, you would need a colored screen, so I designed all this independently. I didn't use any references, so these hex pass-through decoders are all mine. This kind of register for overdrawing pixels was mine. A lot of these things were all mine because I just wanted to do everything from scratch. Now, apart from this, though, I just took this hex to binary from Matt Batwings, but it's a very simple design, and other people have made these for like hex to binary cache layouts on CPUs and stuff, but I thought this would be nice to put here. And it was fairly simple. I just do some synchronization, and then the data rides up these torch towers. And this is kind of dope because you can basically pipeline this entire thing. You can pipeline the data and it goes in. And really, the latency doesn't really matter when you're at a very high tick rate. The thing that matters is your throughput. You want fast throughput. So we have 3 pass-through decoders for that. And yeah, again, it's just the same thing. We got queues and the line calculating hardware. And yeah, after that, I was pretty satisfied with the quad-based texture rendering, because that's what I found out at the end. It's basically quad-based texture rendering. Verlio kind of pointed out that if you drawed like a checkerboard pattern, there'd be like a curve, which is fine though, because if you're at a low res, using a fast rendering algorithm is okay, I think. But anyways, we're gonna go ahead and move on to the next item, which is probably the more cool thing. All right, guys. So this is probably one of my I wouldn't say the greatest accomplishments, but it's definitely something that I don't think anyone else has done, is make a 3D transform done in this amount of space. I mean, it's quite small. I could be wrong, but I haven't really seen anything this small. Now, obviously, I've done a few things, like make a very tiny sine and cosine table. In this case, I basically just reduced it down to 5 bits per item, or per element, I guess, of the sine and cosine. This thing, by the way, this was very stripped down. For 8-bit hardware, this was kind of ridiculous how stripped down I made it. But basically, what I found out with it was I could do basic, like, projections in front of the camera to a certain degree. Like, if I zoomed the Z out far enough away, it would kind of look weird due to overflow. So basically what you could do with this 3D hardware was just like basic like object manipulations in front of the camera, but you couldn't like translate it crazy far away. But what this hardware did help me with is figure out what was kind of needed to make the next iteration, which I gave a little bit more precision. Instead of strictly using 8-bit, I used a 16-bit multiplier, but of course the output was still 8 bits. I still handle 8-bit numbers, but internally I gave it more precision. Another cool thing about serial hardware is that all the data is preserved until the output, because we cut the output off at a certain time, but all the data for the multiplications and adds don't get chopped off like your basic adders or multipliers would do. So that was kind of huge. We could preserve data. But I'm going to go through each step of how the 3D transform works. So basically what I did is I made these 2 high stackable serial multipliers, which might be kind of hard to see. I wonder if I have a... I might have one somewhere. Give me a moment, guys. Here we go. So here's 4. I think this is 3 or 4. 4. So here's 4 serial multipliers on top of each other. So we've got, you can just imagine this top slice as the 2-block high stackable part, but basically we've got the serial ladders here, and they basically go into like a tree structure until the final output, and that's done for your partial products. And then at the very beginning here, we handle all of those binary shifts in serial with this simple delayed enable line, as you can see. As I explained before with serial, all you need for shifting is delays. So if we want to do left shifts, we just have delays this going this way for the inputs. So that's basically that. So that's your B. Now, the A input comes in serial, though, so I can't really showcase this, but I'll link a video to the predecessor of the serial multiplier, because I think it'll give you a better idea of how it kind of works. And then I also have a world download to that specific design. But, okay, so I use those, and I basically do a rotation matrix operation. So I take the initial x and y coordinates, I multiply them by the sine and cosine in a matrix multiplier. In this case, it's a 2x2 matrix. So you're taking the x and y from the vector and you're multiplying it by a 2x2 rotation matrix. So you've got one input being your sine and cosines, which multiply with the x and y's. And then over here, sorry, it's kind of hard to see. It's quite small. But over here, we have those final sums of the matrix multiply, because you multiply and then you add across. It's like multiply down and then you add across. And then those just feed back into the next one. So this one was a pipelined 3D transform. It would first do the rotate x, z, and then y. For weird reasons, I don't know why I had the rotate z here, but the order does matter. You could still do all the necessary rotations for a transform, but it's nicer to have your rotate x, y, and z in that order instead. And that's what I ended up doing with my final 3D unit. But you can imagine these 2x2 matrices multiplying and then pushing the result to the next matrix. And then over here, instead of using a matrix for the translate and the scale independently, I just optimized it so that it only uses 3 multipliers and then the 3 adders. So you could do your scale and then translates. And then at the top for projection, I just use a lookup table for 1 over z, but to a certain accuracy. And then I basically just do like a times 1 over z calculation to do that divide. Now, while this worked for low precision stuff like I mentioned before, where you're just like rotating an object in front of the camera, this kind of precision is not really good when you want to translate the object far away from the camera. And that's something I fixed with my newest 3D unit. And yeah, I also don't use this type of projection method anymore. I actually came up with another one that I'll get into. But yeah, basically at the very top, I'm sorry, it kind of sounds like gobbledygook, but at the top we have our projected x and y coordinates. And you basically sequentially get those to draw out an object, and then you connect the points with lines. Like that wireframe pyramid. With that, I had all the data points, assuming I calculated it before. But yeah, so that was my prototype for the 3D renderer. And yeah, it was actually a very huge contributor to my final design, so I'm very happy with it. We'll go ahead and look at the next thing. Oh, and also, if you go into the OR Discord, under projects, if you type Spirgu, I have all of these like tests on my project page. It's pretty long. You could probably see all the updates I did there. But yeah, I did a lot of work on that. Now we're going to go ahead and look at the final thing before I took a break from this project. All right, so this was my last project. Believe it or not, it was unfinished. Probably one of the first unfinished projects on this graphics hardware journey I've been on. But this going through and building this layout and testing it gave me a lot of insight. So I'm going to go through the things that worked and didn't work. So, oh, and also I'll talk about inconveniences that I've basically fixed. So a huge inconvenience that I hated about this is another reason why I kind of scrapped this, was because it was just so inconvenient to input stuff. So one of the inconveniences I fixed is all this input being separate, like having random levers for your scale over here, having random levers for the translate down here, as you can see. And also just making this easier. I just used pistons so I could see what I was using for these tests back then. But yeah, I had just levers everywhere there. It was really inconvenient. Now I literally use only a tiny bit of serial lines to input. We'll get to that other unit, by the way. So we had the 3D transform hardware. It would output its data here. Then it would get queued into the... this was actually a newer Polygon and colored unit. I modified it for a larger screen. And it also needed to calculate the Z coordinate because what I did is I played around with this Z buffer prototype that I made. I guess I'll have to show that. So basically right here, I had pass-through decoders, and then let's see, I had a Z buffer. So this looks like just the basic overwrite memory from before, but it's actually a Z buffer and then that memory combined. The Z buffer just compares signal strength, and it's configured to choose the closest Z coordinate. But the precision, with the way I was implementing it, I didn't implement it smart here, because I was taking the Z coordinate from every single pixel of the polygon. But for something with this low precision, I would have been better off just getting the average Z coordinate of the quad and using that instead, because then it would space out the Z is actually a lot better for that precision. So that's what I'm doing now. But yeah, this project helped me a lot kind of get the hang of hex a little bit better. I also did some very quirky things like oscillating different towers because I was using 5 hertz. So I made some tech that basically would oscillate like 2 sets of decoders so it could use torches. It was kind of weird. That's probably another reason why I decided to halt. But it actually worked pretty good. I was pretty impressed for the size and everything. It was a pretty cool technique. And yeah, it's basically the same thing. You have your texture port input here. And yeah, it'd be a pain in the butt to demonstrate it drawing something coherent. But yeah, I did a lot of cube renders, and obviously the Z was the problem. So, yep, I basically scrapped this. I even found these kind of things out when I made a software version of this project, because I didn't make a software version of this before. Now I did that, and that's basically something I fixed. So yeah, basically after this, I was like, you know what, I'm going to take a break. I'll just let the thoughts run in the background, and when I get inspired, I'll start work on the next iteration. So yeah, while the polygon and texture unit worked, and the 3D unit worked, my Z buffer implementation was just kind of stupid. Input-wise, the actual buffer itself can still be good. I just had bad input. So now we'll go ahead and move on to the present, where I took a different approach to testing, where it's a little bit more automated. All right, so I'm back. It's been a few weeks since I last recorded the last segment, but here we are. We're on the new one. So this device was a testing rig to test all of the hardware I can use for 3D math and stuff. So I have a few things that I will go over, and then we'll proceed. So basically what I did here is I just took an old ISA I made, a very simple one. I used it to make a simple CPU. I got the ALU here with an input and output port and the 4 general purpose registers, and it's small because it's serial, as you would expect. So that, then right here I made something that I call the function port. And basically the way it works is you input an address, and then you can actually feed serial data out sequentially to one of these torches. So I have that. Over here I just put some ROM here for memory. program memory, and then I have some RAM here, and the RAM is completely separate because it's handled by the... Well, actually, no, not in this case. In my next project that I'll have to start showing, that one had the RAM separate. But yeah, I built this whole thing to test different functions like line drawing and stuff, and it worked. But then for this 3D part, since I literally made it activate with the simple object address, I didn't really need to use the CPU much. So yeah. Anyway, so I had that, and I've got a better one in the works right now. So that'll be cool to show in the future. Right here in the middle, sorry that's a little bit messy. I actually am doing a lot of changes, but right here in the middle, I actually built 4 3D transform units. These are my own design, and I use 2-block stackable multipliers here. These are 16-bit multipliers, I believe. Yeah, these are 16-bit multipliers for serial mult. And I have... There's just a couple of them stacked like this. I think there's 1, 2, 3, 4, 9. So there's 9 of those. And then there's adders for doing the matrix, to complete a matrix mult. Because what it does is it does matrix mult for all the rotations, and then scale and translate are done in a more optimized way. And then up here, I have basically hardware that does a very, very cheap perspective projection calculation. It's not fully the weak perspective projection, but it uses actually some it uses some math to do a iterative approximation of 1 over z. But I have it only set to 1 iteration. And the method I used was Newton's method. I basically did the Newton's method of 1 over x function, and then I optimized it for binary shifting, so it could be very fast, and it only uses 1 subtraction. And the precision is honestly good enough for a 31 by 31 display, so I rolled with it. So we got 4 multipliers, so or no 4 3D units. Now down here, I showed this in a other video, but I have a very fast line drawer. As a matter of fact, I'm able to generate. I'm able to have a good time complexity of log n due to the nature of it exponentially becoming faster. The only thing is I do handle the output sequentially simply due to me wanting to use one XY decoder. I didn't want to do multiple XY decoders like before, so I just used one. And the reason is because I'm still generating the lines every 10 seconds, which is still faster than the other hardware, obviously. So I had no need to make it any faster. So yeah, basically, this testing unit, all it does is 3D wireframe rendering, and I'm going to demonstrate that in a moment. Oh, and another thing I added here, this is also another device I made. So this is the object memory. So what you do is you input an object address. So the first object at address 1 is a pyramid. And basically the way the objects are read out is it's a linked list. So you have your first vertex and edges, then it'll go to the next one, and the next one, and the next one. And then once it reaches the end of the linked list, it goes to a state where it doesn't operate anymore. So it goes to the 0 address. But yeah, basically, you can think of this as like the first node of the linked list, 2, 3, 4, 5, and then it ends here, it goes back. Then if I wanted to access the cube, I would go to address, let's see, 1, 2, 3, 4, 5. So the pyramid ends here, the cube would start here, it iterates through the cube until it gets to the end, and then it goes back. So they're basically segmented linked lists. And then in serial, they sequentially output. So if I remember correctly, the red, orange, and yellow is my XYZ coordinate. And then following, we have the edge. This is the edge data. I actually store 3 edges per XYZ coordinate because it's a pretty decent way to handle it. And obviously, the way the edges are grouped can be in random order because they just point to the ordered XYZ coordinates that calculate. So this yellow, or this line over here for the edges, goes into a serial stack that I designed. So basically every register is a serial register, and it can actually push and pop off of this. And it's very easy to stack, as you can see. I made it so that you can store a total of 48 edges, which is honestly overkill for something this simple. But this is something I might reuse in the future because it's such a good piece of tech, even in general, just to store data. As you can see, the push is serial, and then the pop is serial. Now, when you do a pop, the edges go on this blue line. To the vector. This is a vector that actually stores the results of the transformed vertex. So this will be the projected x and y coordinate stored here, and it basically acts like a C++ vector. You could push to the back of it, but you can also address it like in an array. So the edges are the address of this vector, and then the xy coordinates simply feed out on a single line, like this, back to back. You have your xy, xy. You send two points here in serial on the single line, and then it goes into the line drawer and calculates the line. So, okay. I'll do a final breakdown real quick, and then we'll actually see it run. So, again, this is just a CPU for automated testing. Nothing crazy. Then we have our 3D units. In the future, I only need actually one 3D unit because my polygon and texture unit will not be able to keep up with one, which is like barely, which is awesome. So I'll need less of those. Then yeah, down here, object memory, and then the edge stack. And also, I may not need the edge stack in my future project. I just think it's good for other applications because you can store other data in there. And yeah, function address. And the screen. And the screen has a very simple, it's not obviously the best way to do the screen buffer, but I got a simple screen buffer there. Alright, without a further ado, let me go ahead and demonstrate how it, or where the transform data is input. I'll need to make the tick rate high, because it takes a bit over 3 minutes in real time to calculate the object onto the screen, so I'd rather not wait. So let's see. Yeah. The first input is the translates. In this case, with the cube, I don't have to input any translates because we're gonna... The way the weak perspective projection works is it doesn't need you to translate out from 0. The only thing is you don't want the z-coordinate to be minus 32 in this case. So I'm gonna go ahead and just input zeros for all of the I need to count. I'm sorry. 1, 2, 3. Okay. So I put in the translates in serial, and now we can put in the rotates. I'll do a rotate of 45 degrees. In this case, I'm using a pi over, I believe it's a pi over 8 times the input, so that gives me different increments of the radian. So I'll go ahead and put a rotation of 45 degrees on every axle. And we could try some other ones too. I'll do some other tests for you guys. And then the scale, I'll set the scale to 1. Now, it may look like I'm inputting 16, but you have to remember inside the... Well, you haven't remembered this to begin with, but inside the 3D transform unit, the data actually isn't fixed necessarily. It's only fixed on the input and output, but not in between. So, 1, 2, 3. Okay, so that's that. So I got the transform variable set in place, so we did the translate input, the rotation input, and the scale input. So it's really nice. They all travel in serial. You only need one bus to do it all. And if you're wondering that it'd be super hard to re-input these values, it's not really, because you only need to do this once, and then you're going to do a batch calculation of vertexes for an object. So it's not super bad. And of course you can have hardware that makes the input easier. Now, over here I'm just going to roll with this input. And we'll go ahead and render our object, which is a rotated cube. So right now it's storing the edges, it's basically pushing them onto the stack, and then at the same time it's already starting the 3D calculation of each of the vertexes. We only have 8 vertexes to calculate here. But yeah, they basically are, all the vertexes are being pushed onto the vertex vector over here. And then after they're all handled, it'll go ahead and line draw. So I guess we'll go ahead and just wait at the front here until it renders the cube. It's already starting to push the lines onto the screen buffer. So we're almost there. And there we go, rotated cube. How cool is that? Let's do no rotations. Let's just see the cube facing frontward. I think that'd be an interesting one. So I'll go ahead and just input the data. So it's hard to predict how fast it takes, because even with the speed ups, it's not perfect. But it'd be a lot better if I ran this on MCHPRS. I plan to run a better model on there. But there you go. There's the cube facing forward, no rotations. So let's do another one where I translate the cube out. Alright. And there we go. So there's the cube super far away, basically. It's pretty way out there. It's tiny. Because I literally translated the cube like 24 out. And if I translated it like 48 out, it'd actually become a tiny dot on the screen. So, yep. It's kind of hard to see this far away, but there's the top, and then there's the sides of it. And then the base just looks flat because of the rotation. But yeah, so there you go. Yep, you can render it way out there. It just makes it looks funnier the more you go out, obviously. Okay, so I guess I'll show you what I'm currently working on next. Okay, so basically this is where I've left off next. So yeah, down here I actually have a more optimized or better it's not necessarily more optimized, but it's a more efficient version of that Polygon unit from before. So as you can see, what I did is I actually took my line calculation circuits and I stacked them 2 blocks on top of each other. So what this does is it does a bunch of linear calculations for lines, and then it uses those lines to construct the texture coordinates, and it also uses the data to construct the polygons. And then the data just simply goes out here to the simple output. I need to turn this off. Because right now, nothing's really... There's no reset on that. So it goes on the output, and then the data comes out as... I believe this is the U and V coordinates. They should hook into the texture input here. Yep, UV coordinates. And then down below, I've got the Z, X, and Y coordinates. So it's X, Y, Z, but they're just ordered a certain way because it was easier to do it this way. And then I believe I actually cut this off because of that thing I realized later about the average Z. So I cut this off, but I left it here as a possible usable part. So, you never know when you're building and changing things. You want to keep certain stuff just in case. But what I plan to do is I plan to actually have the Z coordinate average feed here using a 4-bit approximation, but it's going to be shifted into a certain range that's optimal for my viewing distance, because I have to define a viewing distance on the frustum and then deal with the objects like that. But so I'm going to store the Z coordinates there in the future. Now the projected X and Y coordinates simply go onto here. Well, this is the coordinates of the quad, rather. You have your projected X and Y in the input there, but then your quad coordinates come out here. Quad or triangle, depending on what you're rendering. So they go in the back here. And then in the middle here, I actually have that simple Z buffer from before. So that's right there. And that's used to enable the drawing, actually. So this is the color coordinates, I believe. Yeah, this is color coordinates. Not color. What am I saying? Sorry, it's been a while. No, this is my color value using the quad coordinates. And then let's see. Oh, and then these are my Z values, I believe. Yeah, Z coordinates. These are the Z coordinates that feed into the back here. And they also use the quad coordinates to go to the right Z register. And it always chooses the closest Z coordinate. The way it does that is it actually chooses the furthest one, but we're doing an invert on the data, so it reverses the order. And then it enables the drawing of each pixel. Now, since I wanted to keep this device simple, I kept the pixel plotting at 3 redstone ticks per pixel, which is honestly good enough. When you use a mod to speed the game up, you won't even notice it really that much. So I'm not worried about that. And this is just a register that allows you to paint over the previous. But eventually what I plan to do is move this out a bit and then add my screen buffer here. But for now, we can just see the individual pixels render. Now up here I was playing around, I was thinking, oh, I might use the quad 3D unit, but as I mentioned before, I'm actually just going to use 1, because I realized that 1's enough when I did the speed calculation of this. So we'll be able to get all the coordinates before this finishes, barely. And this will also make the Z averaging component easier. But yeah, no, we're just gonna go ahead and showcase this right now, the actual texture, or the actual quad rendering. And now I'll just start the calculation. Yeah, don't mind these, that's just because of the texture pack. But yeah, it's gonna go ahead and quickly render whatever we input. I didn't really do such a good job planning the inputs right now, but that's okay. So it looks like we're gonna draw some kind of weird quadrilateral that's diagonal. So this will be interesting. And yeah, we had the x coordinate like 30, something like less than 31 and such, so we'll see what happens. It's probably gonna be like a trapezoid, who knows? We'll find out. The nice thing about this new Polygon render is it can actually fill the entire screen if you wanted it to. So it accounts for the total range of the screen. which I'm very happy with. Because the project Speargo from last year, it could only do quads that are like a max size of like 20 on the X and 20 on the Y. It's kind of weird. But not with this one. This one's pretty great. Yeah, it looks like I did a trapezoid. That's interesting. I guess the coordinates make sense. And yeah, as you can see, it's stretching the brick texture because normally it would just have the brick line just like that, but it's like stretching it right now. Just kind of interesting. Yeah, and obviously, the more stretched your texture, the funnier it can look in some cases. But I guess that's it. So it just did like a trapezoid. I could also render a square object, so maybe I'll do that as well, so you can see it. There's a lot of colors. There's 16 colors. It's yeah, it's not crazy. Okay, but here we go. So this will just be some kind of square, hopefully. Yeah, it should be like somewhere approximately like this. So this will be cool to look at. And yeah, all the polygons take the same amount of time to calculate, just no matter the size. But that's okay because it's actually pretty quick. You may not think that. I think it takes a bit over 4 minutes to render this in real without any speed ups. So if you think about it, if you speed the game up like a crazy amount of times, that's basically near. It's really fast. But I'm only making the tick rate 1,000, which means this is like only 100 times the speed. But it's actually not quite because the game it doesn't actually accurately do the tick rate. So no, I'll have to throw this on MCH PRS someday. There you go. I got a funny brick texture. Is it done yet? Yeah, it's done. Cool. Got a funny brick texture. I didn't really do the brick texture that good here. So there you go. Anyways, so that's my progress. So I built a polygon and texture mapping unit for very cheap texture mapping. Nothing crazy. I've got some hardware for 3D calculations. I'll probably go ahead and show you one of the ones that are isolated. Oh, there it is. Is that the? Let me see if this is the correct copy though. Yeah, this one. So this is it on its own. It's actually probably one of the smallest 3D transform calculators out there. So I'm pretty proud of it. And I was challenging myself to make one that could fit within a 3x3 chunk area, but that one's still in the works. So that might be a while before that one is done. That's like a side project, but this one's very great. So yeah, this one has the lookup table for sine and cosine, but I was thinking about using K-maps because I finally figured out a very great way to optimize the K-map terms. So that's what I was actually doing on my my little challenge project. I built a K-map of sine and cosine on the OR server. Oh, I guess we'll have to go to the OR server real quick so I can show you what the next testing unit is. Okay, so we are on the OR server. I got program ROM here. And yeah, the RAM is now completely separate. There's literally a function port output for it. So you have RAM read and RAM write. I guess I have to explain how this function port works now. Again, it uses the address. It uses an address, and then you can get an output in serial on any of these port pins. And then something I have here is I just have some basic memory, an input and output port. And then right here, I have a special register that I call the return register, which can return a byte value. And it also returns a branch. So this is how you can make it Turing complete. You can basically make an ALU, an external device, and you can have the branching data come out on this register. And while that's a slower approach to computing stuff, it's a way more flexible approach because now I can have any external device induce a branch. So that's going to be cool. I can't wait to show you guys this device when I hook up the 3D hardware over here. That's what I've allocated the space for. Oh, this was my challenge build. For some reason, I put it in the way, but yeah, believe it or not, this is the sine and cosine K map. It's very tiny. Anyway, so yeah, no, so in the future, my next video should be the color screen hardware with the 3D unit. And I'm gonna have to make some memory again for the object mem, so I might have that somewhere here, so I could store the object and its texture coordinates. And also the address for like a part of the texture coordinates will probably use a part of the texture input port. I need like a cache for the textures, so that should be cool. And yeah, again, this computing unit only has 4 instructions. I think I have them somewhere. Do I? Ah, that's it. So there you go. No op. Just mem a equals in, out equals mem, and out a equals nb. And that's all you need. You just put capable external devices, and you can compute anything you want. So yeah, that's gonna be so awesome to show. But anyways, that's all I've got to share for now. That was like a year's almost. I didn't show everything, by the way. I just showed like the highlights of what I've done over the year. So that's about it. Um, some other things I might share with you guys is carry look ahead adders because I actually made one last year that is so cool. I'll have to show it. But yeah, thank you for watching. Sorry the video was long, and I hope you'll like to see what comes in the future.